There are galaxies so far away that their light began travelling toward us before Earth had oceans, before the sun fully ignited, before anything we would recognise as home even existed. And now, the most powerful space telescope ever built has found some that seem too old, too bright, too fully formed, impossibly mature for the age of the universe itself. They should not be there, not like that, not so soon after the beginning. And yet, they are. Which forces a question that sounds less like science and more like trespass. Are we looking at galaxies born in another universe, bleeding into ours across a boundary we were never meant to see? We used to think we understood the early universe. After the Big Bang, 13.8 billion years ago, space expanded, cooled, and gradually allowed matter to clump. Hydrogen formed first, then gravity sculpted it into stars. Stars forged heavier elements. Galaxies assembled slowly, like cities rising from scattered villages. That was the timeline. Then the James Webb Space Telescope opened its golden eye. JWST doesn't look like a traditional telescope. It doesn't see visible light. It sees infrared, the faint, stretched glow of ancient light that has been travelling for billions of years, pulled longer and redder as space itself expanded. It is tuned to catch whispers from the edge of time, and almost immediately it found galaxies that appear to exist just 300 to 500 million years after the Big Bang. To understand why that matters, shrink the universe's entire history into a single year. The Big Bang happens at midnight, January 1st. Earth forms in early September. Dinosaurs vanish on December 26th. Humans appear at 11:52 p.m. on December 31st. Now imagine discovering a fully grown city on January 4th. Not a few huts. Not scattered lights. A skyline. That's what JWST saw. Massive galaxies containing billions of stars, already shining when the universe was only 2 to 3% of its current age. Some appear as massive as the Milky Way. Some seem even denser. In our models, galaxies weren't supposed to grow that fast. Gravity needs time, stars need time, structure needs time. Yet here they are. You can feel the tension. Either our understanding of cosmic evolution is incomplete, or something deeper is happening. The first explanation scientists consider is acceleration. Maybe early star formation was far more efficient. Maybe gas collapsed faster. Maybe black holes seeded galaxies earlier than expected. Perhaps the early universe was more turbulent, more violent, more productive than our simulations allowed. That alone would be revolutionary. But some researchers have dared to step further. Because when you measure the light from these galaxies, you don't just see brightness, you see redshift. Redshift is our cosmic yardstick. The more space stretches, the more the light stretches. High redshift means extreme distance. Extreme distance means extreme age. Some of these galaxies have redshift values that push against the boundary of what we thought possible. And here is where the idea becomes electric. In certain cosmological models, particularly those involving inflation, the early universe did not simply expand. It may have expanded explosively, exponentially, in a fraction of a second. Inflation solves many problems. Why the universe is flat, why it's so uniform, why tiny quantum fluctuations became the seeds of galaxies. But inflation comes with a strange side effect. It might not have stopped everywhere at once. In some regions, space could have continued inflating, creating separate bubble universes, each with its own physical constants, its own expansion rate, its own properties. A multiverse. Most versions of this idea keep universes completely separate, like soap bubbles drifting apart, never touching. But some models allow for something more dramatic. Bubble collisions. If two young universes formed near each other in the early inflationary chaos, they could have brushed, intersected, left scars. Those scars could imprint unusual patterns in the cosmic microwave background, the afterglow of the Big Bang. Scientists have searched for these signals for years. Now imagine something else. Imagine that in the earliest moments, the boundary between universes was not perfectly sealed, that density fluctuations, regions of compressed energy, bled across. If a neighbouring universe had slightly different physical conditions, perhaps faster structure formation, slightly altered gravity, different initial energy distributions, its galaxies could mature more quickly. And if even a fragment of that structure intersected our observable region, what would we see? Objects that look too old, too massive, too early. You don't need to believe that's what's happening, but you can feel why the idea won't die. Because the alternative is equally profound. That our understanding of the first 500 million years of cosmic history is incomplete at a fundamental level. Either way, the universe just became larger. Not in size, but in possibility. Stand with me for a moment inside one of those early galaxies JWST captured. Its stars are hotter, bluer, and shorter lived than ours. Massive stars burn fast, living only millions of years before exploding as supernovae. Those explosions seed space with carbon, oxygen, iron, the ingredients of planets, of biology. In these galaxies, that process seems to have already happened. Rapidly. It's as if the universe sprinted before we thought it could walk. And we are tiny witnesses. On a rocky planet orbiting a quiet star, we build mirrors coated in gold, unfold them 1 million miles from Earth, and point them toward darkness. We catch ancient photons that have been travelling since before our solar system existed. And those photons whisper, something unexpected happened. The human frame matters here. We're inside it, trying to reconstruct its childhood from fossils of light. Every image JWST sends back is a time machine, not a metaphor, a literal capture of history. When you look at one of those galaxies, you are seeing it as it was billions of years ago. If it still exists today, it has evolved beyond recognition. But we never see that version. We see the young one. Except now, the young ones don't look young. They look seasoned, weathered, fully structured. It's as if we opened a baby book and found photographs of adulthood. That dissonance is the crack. And through cracks, new physics sometimes enters. Some theorists suggest modifications to dark matter behaviour in the early universe. Others propose variations in star formation efficiency. Some even question whether redshift alone tells the full story at extreme distances. And then, at the edge of speculation, there is the whisper. Another universe. Not science fiction. Not fantasy. A consequence of inflation equations taken seriously. If the cosmos is not singular, but plural, if ours is one region in a vast foam of expanding realities, then what we see at extreme distances might not only be far away. It might be adjacent. Light from another universe would not travel through empty space in the way ours does, but gravitational imprints, quantum boundary interactions, or relic density patterns could masquerade as anomalous structures. And JWST's galaxies are anomalous enough to invite the question. No one is claiming proof. Scientists are still uncovering what these early observations truly mean. Data is refined, spectra are analysed, mass estimates are recalculated. Some galaxies once thought impossibly massive are being revised downward as measurements improve. But not all tension has disappeared. The early universe remains strangely productive, which means we stand at a frontier, and frontiers are where human imagination and hard measurement meet. We built JWST to look back in time. It is doing that. What we did not expect was that the past would look back at us with something unfamiliar in its eyes. Something that suggests our cosmic origin story may be more layered than we believed. Maybe the universe matured faster than we thought. Maybe gravity was more efficient. Maybe star formation ignited with ferocity. Or maybe, just maybe, what we call our universe has neighbours. And at its farthest edge, where time thins and light stretches into invisibility, we are seeing not just distance, but contact. Contact does not have to mean collision. It does not have to mean portals or tears in space. In cosmology, contact can be subtler, an overlap of influence, a boundary condition written into the earliest moments of expansion. When inflation ended in our region of space, it may not have ended everywhere. Other regions could have continued inflating, stretching beyond comprehension, birthing their own cosmic histories. If two such regions formed close enough in the primordial chaos, their edges might have pressed together before racing apart faster than light could ever follow. We would not see another universe the way we see a galaxy. We would see the consequences. To understand why that matters, picture the observable universe as a sphere around us, about 93 billion light-years across. That number is already absurd. If you travelled at the speed of light, non-stop, from the birth of the universe until today, you still wouldn't cross it, because space itself expanded while you moved. Now imagine that entire sphere is just one bubble in a foam of others. Each bubble expanding. Each bubble governed by physics that might be slightly different. Slightly stronger gravity. Slightly heavier electrons. Slightly altered dark energy. Tiny differences in the early seconds could cascade into massive differences billions of years later. In our universe, it took hundreds of millions of years for gravity to gather enough matter to form large galaxies. In a neighbouring one, if density fluctuations were larger, if matter clumped more aggressively, galaxies could ignite faster, grow faster, mature sooner. Now imagine the boundary between these regions during the first fractions of a second. Inflation is violent. Space doubles in size again and again in less than a heartbeat. Energy fields fluctuate. Quantum randomness is amplified to cosmic scale. If two inflating regions brushed, their boundary could compress energy in a thin shell. That shell, once inflation ended, would evolve inside one universe as a region of unusual density. Fast forward 13.8 billion years. JWST looks toward that direction, and it finds galaxies that seem to have grown too quickly. Not proof, but a fingerprint-shaped question. You can feel the scale bending here. We are not talking about distant continents. We are not talking about distant stars. We are talking about entire cosmic histories that may have unfolded parallel to ours. And yet, all we actually have are photons. Ancient photons stretched into infrared, arriving one by one at a mirror floating a million miles from Earth. This is the human paradox. The biggest ideas we have are built from the smallest signals. A pixel brightens. A spectrum shifts. A line in a graph bends slightly upward. And suddenly, we are asking whether reality is singular. Let's anchor this in what we know. When JWST measures a distant galaxy, it analyzes its light spectrum. Certain chemical elements absorb specific wavelengths. By identifying these patterns, astronomers estimate composition, star formation rate, and distance. The earliest galaxies JWST found showed surprisingly high stellar masses. That implies either rapid star formation or a misinterpretation of the light. That would be like finding a fully grown oak tree days after planting a seed. Later analyses have adjusted some of those numbers downward. Some galaxies are less massive than first believed. Some redshifts were refined. The tension eased but did not vanish. Even conservative estimates leave us with galaxies forming stars at astonishing rates. Hundreds of solar masses per year. For comparison, the Milky Way forms roughly 1 or 2 solar masses per year today. The early universe was a furnace. Dense gas, intense radiation, rapid collapse. It may not require another universe to explain that. It may require us to accept that the cosmos was more explosive, more efficient, more extreme than our models predicted. But extremity is exactly where new physics hides. Inflation itself was once a radical idea. So was dark energy. So were black holes. Each began as a mathematical discomfort, an inconsistency in equations, before becoming pillars of cosmology. If multiverse models are correct, then our universe might be one region in an eternally inflating background. New universes constantly bud off like droplets from a fountain that never stops. Most would be causally disconnected forever. But forever, in cosmology, depends on geometry. Some models suggest that if a collision happened early enough, its imprint could still be observable today, as temperature asymmetries in the cosmic microwave background. Scientists have searched for circular patterns, signatures of past bubble collisions, in data from satellites like Planck. Nothing definitive has been found, but absence of evidence at that sensitivity does not eliminate every scenario. And now JWST adds a new kind of anomaly, not in background radiation, but in structure formation. It is not screaming, "Another universe." It is whispering, "Something unusual happened early." We stand at the edge of interpretation. This is where narrative temptation grows dangerous, but also powerful, because the multiverse is seductive. It expands the stage beyond imagination. It suggests that everything we call reality might be one instance among countless variations. But physics does not move by seduction. It moves by constraint. Any multiverse explanation must be consistent with observed cosmic expansion, with nucleosynthesis, with the distribution of large-scale structure, with gravitational lensing, with everything else we measure. That is a brutal filter. And yet the idea persists, not because it is dramatic, but because inflationary mathematics naturally allows it. If eternal inflation is correct, universes are not rare accidents. They are inevitable outcomes. So what would it mean if JWST's farthest galaxies were influenced by another universe? It would mean our cosmic horizon is not a wall, but a seam. The observable universe is defined by light travel time. We can only see as far as light has had time to reach us. Beyond that lies more universe we cannot observe. But beyond that, even further, there could be entirely separate regions born from the same inflationary background, yet causally disconnected from us forever, unless the earliest moments left cross-boundary scars. Imagine standing on a vast plain of fog. You can only see a few hundred meters in every direction. That circle is your observable world. But beyond the fog lies more terrain, and perhaps, somewhere in that unseen expanse, another plane collided with yours long ago, leaving a ridge at the boundary. You cannot see the other plane, but you can see the ridge. JWST may have found ridges, or it may have found that the plane itself was more rugged than we imagine. Either way, the simplicity is gone. The early universe is no longer a quiet, gradual dawn. It is a storm, and we are only beginning to map its lightning scars. Storms leave patterns, not random chaos, patterns written in debris, in pressure gradients, in shock fronts. When astronomers stare at JWST's deepest fields, they are not just seeing scattered galaxies, they are seeing structure, clusters, filaments, hints of a cosmic web already threading itself together when the universe was barely out of infancy. That web matters. Gravity does not build evenly. It amplifies tiny irregularities. In the first 380,000 years after the Big Bang, the universe was a hot plasma, opaque, dense, glowing. When it cooled enough for atoms to form, light finally travelled freely. That fossil light is the cosmic microwave background. It shows us faint ripples, temperature variations of 1 part in 100,000. Those ripples are everything. They are the seeds of galaxies. Every star, every planet, every cell in your body traces back to those microscopic fluctuations. And according to our measurements, those fluctuations were small. Small ripples should take time to grow. So why do we see such massive structures so early? One possibility is that dark matter, the invisible scaffolding that makes up about 85% of all matter, clumped faster than expected. Dark matter does not emit light. It does not interact electromagnetically. It responds to gravity and little else. In the standard model of cosmology, dark matter begins collapsing into halos first. Gas falls into those halos, stars ignite, galaxies emerge. If dark matter behaved slightly differently in the early universe, if it interacted more strongly with itself, or cooled more efficiently, it could accelerate structure formation. That explanation stays within our universe. But there is another layer. Inflation did not just expand space, it magnified quantum fluctuations, tiny, random variations in energy fields. Those fluctuations became the ripples we see in the cosmic microwave background. In most regions, they were modest. But what if, at a boundary with another inflating region, those fluctuations were amplified? Imagine two expanding bubbles pressing against each other. The boundary between them would not be smooth. Energy densities could spike. Fields could interfere. When inflation ended, that boundary could freeze into our universe as a region with enhanced density contrast. Enhanced density means faster collapse. Faster collapse means earlier galaxies. From our vantage point, billions of years later, we would simply see galaxies that appear too mature. Not because they travelled from another universe intact, but because their birth conditions were influenced by one. This is the subtle version of the idea. No portals, no crossing of stars. Just altered initial conditions written into the fabric of space before space settled down. You can feel how delicate this is. We are standing at the edge of measurable reality, trying to infer events that happened when the universe was less than a trillionth of a second old. And yet, we do it, because physics leaves trails. If another universe influenced ours, it would not rewrite all of physics. The constants we measure, the speed of light, the strength of electromagnetism, the masses of particles, appear uniform across observable space. That uniformity is powerful evidence that we are not seeing wholesale contamination from a radically different cosmos. But slight differences in early energy density do not require different constants. They require different circumstances, and circumstances can change everything. Let's bring this back to you. You are sitting on a planet orbiting a star that formed 4.6 billion years ago, in a galaxy that took billions of years to assemble. Every atom in your body passed through multiple generations of stars. Now imagine that the galaxy you live in exists because of fluctuations imprinted at the beginning of time, possibly influenced by events beyond our observable horizon. Your existence could be downstream of a boundary interaction between universes, not proven, not confirmed, but physically conceivable within certain inflationary frameworks. The scale is disorienting. We are used to thinking in causes we can trace. A storm forms because warm air rises. A species evolves because mutations accumulate. But here, the cause could be an inflationary fluctuation triggered by adjacent space-time domains before the universe even had particles. And all we see now is the result: galaxies that grew up too far. There is another angle. Redshift does not just measure distance, it measures expansion history. The relationship between redshift and time depends on how fast the universe expanded at different epochs. If early expansion behaved slightly differently than assumed, if dark energy had a dynamic component, or if gravity deviated subtly at high energies, then our distance estimates could shift. That would mean some galaxies are not quite as impossibly early as they appear. Recalibration is ongoing. Spectroscopic confirmations refine the numbers. Some initial photometric estimates overstated redshifts. Science corrects itself with brutal honesty. But even after correction, the early universe remains startlingly luminous. Star formation rates at redshifts above 10 are higher than many models predicted, and that alone forces revision. The multiverse idea is not a default conclusion, it is an outer edge of interpretation. Yet it lingers, because inflation, our best explanation for the universe's smoothness and flatness, naturally suggests that what we see may not be the whole. Eternal inflation proposes that space is still inflating somewhere right now beyond our horizon. New universes are continuously forming, each potentially with different properties. If that is true, then our universe is not the entire story. It is one chapter, and JWST, by pushing observational astronomy deeper than ever before, is skimming the margins of that chapter. When we look far enough, we approach the surface of last scattering, the limit beyond which light cannot reach us because the universe was opaque before that. We cannot see past that wall, but we can see almost to it. And near that boundary, anomalies matter more, because there is less cosmic time for complexity to develop. If complexity is already present, something accelerated it. Either physics was more efficient, or initial conditions were more extreme, or both. Here is what makes this moment extraordinary. For most of human history, the question of other universes was philosophical, speculative, untouchable by experiment. We built a telescope to study first light. Instead, it may be forcing us to reconsider first cause. And the emotional weight of that is not abstract. It means that when you look up at the night sky, the darkness between stars may not simply be empty space extending forever. It may be a boundary of perspective, beyond which reality continues in ways we are only beginning to imagine. Yet we are not powerless observers. We are decoding infancy from fossils of radiation. We are testing models against photons older than Earth. We are refining simulations to see whether ordinary physics, pushed harder, run earlier, allowed to be wilder, can account for these galaxies without invoking neighbours beyond our cosmic bubble. That work is happening now. Data streams in. Models adjust. Hypotheses compete. And somewhere in that process, the truth tightens. Whether the answer is accelerated structure formation or the faint echo of another universe brushing ours at the dawn of time, one thing is certain. The early cosmos was not gentle. It was ferocious. And we are only just beginning to understand how ferocious it truly was. Ferocious means fast. Not just bright, not just violent. Fast in a way that compresses cosmic milestones into impossibly short spans of time. In the first few 100 million years after the Big Bang, the universe was smaller, denser, and hotter. Gravity had less distance to work across. Gas clouds were thicker. Collisions were more frequent. Radiation fields were intense. Picture a city under rapid construction, not over centuries, but in weeks. Steel beams rise overnight. Concrete hardens in hours. Entire districts appear before anyone can map them. That is what JWST is hinting at, a construction phase that may have unfolded at breakneck speed. When astronomers model early galaxy formation, they feed in known physics, gravity, hydrodynamics, dark matter behavior, radiation feedback. They run simulations on supercomputers that recreate billions of years in compressed digital time. Before JWST, those simulations predicted the first galaxies would be small, proto-galaxies, building blocks, merging slowly into larger systems. Instead, JWST's images reveal candidates for surprisingly massive galaxies already assembled within 300 to 500 million years. Some appear compact yet dense, packed with stars forming at extraordinary rates. If those measurements hold, then star formation in the early universe was not gradual. It was explosive. And explosions require fuel. The early universe had plenty of hydrogen and helium, primordial gas forged in the first 3 minutes after the Big Bang. But it lacked heavy elements. The first stars, known as population 3 stars, were likely enormous, hundreds of times the mass of the Sun. They burned hot and died young, enriching their surroundings with heavier elements through supernovae. That enrichment allows subsequent generations of stars to form more efficiently. If the first stars were larger and more numerous than expected, they could have accelerated chemical evolution dramatically. A cascade effect. Massive stars explode. Gas cools faster with new elements. More stars form. Galaxies bulk up quickly. This is a universe pushing itself forward with urgency. It may not require another universe to explain, but it does require us to accept that the cosmic dawn was brighter than we imagined. Yet there is still something unsettling about scale. Even with accelerated star formation, assembling billions of solar masses in such a short time strains models. And tension in cosmology is not a flaw, it is a compass. When measurements and theory disagree, something new waits in the gap. Sometimes that something is a recalibration of instruments. Sometimes it is a new understanding of astrophysical processes. And sometimes, rarely, it is a shift in the underlying framework. The multiverse hypothesis lives in that outermost tier. It emerges not from fantasy, but from the mathematics of inflation. Inflation proposes that a scalar field, an energy field permeating space, drove exponential expansion in the earliest fraction of a second. In some versions, this field decays unevenly. Some regions stop inflating and become universes like ours. Others continue inflating indefinitely. This creates a fractal-like structure, pockets of normal space embedded in an eternally expanding background. Each pocket could have slightly different vacuum energy, particle masses or symmetry breakings. In many models, these pockets are forever separated by expansion faster than light. But in the earliest moments, proximity could matter. Imagine two bubbles forming side by side in boiling water. Before they detach and rise, they press against each other. That pressure leaves a distortion. Translate that into space-time. A distortion in energy density at the boundary could seed enhanced structure formation in one direction of our observable universe. From Earth, we would not see the other bubble. We would see an asymmetry. We would see regions where galaxies formed earlier, faster, brighter. And that is precisely the kind of anomaly scientists look for. So far, large-scale surveys show remarkable uniformity across the sky. The cosmic microwave background is astonishingly even, with only tiny fluctuations. But remarkably uniform does not mean perfectly identical in every measurable way. Subtle anisotropies exist. Dipoles, cold spots, slight directional variations. Most are explained within standard cosmology. Some remain curious. JWST's deep field observations are still limited to narrow patches of sky. They do not yet provide a full sky map of early structure. As more observations accumulate, patterns may emerge. If early massive galaxies cluster in certain regions more than others, that could signal environmental effects from the dawn of time. Or it could simply reflect statistical variance in small samples. Science advances by expanding samples, by checking and rechecking, by letting data harden into clarity. What makes this moment powerful is not that we have proof of another universe. It is that we have reached a technological threshold where such questions are no longer purely metaphysical. For the first time, our instruments brush against the boundary conditions of cosmic origin. Think about that. For tens of thousands of years, humans looked at the sky and saw points of light. Myths filled the darkness. Constellations carried stories. Now we deploy segmented mirrors the size of a tennis court, align them with nanometer precision, cool instruments to near absolute zero, and place them beyond the moon's orbit to avoid thermal noise, all to capture photons that began their journey before our galaxy was fully formed. And those photons are telling us that the early universe may have been stranger than we allowed. Whether that strangeness resolves into revised star formation models, or into evidence of inflationary boundary interactions, the effect is the same. Our cosmic origin story is expanding. Not in length, in depth. If galaxies formed earlier and more efficiently, then heavy elements appeared sooner. That means planets could have formed earlier. That means potentially habitable environments could have existed closer to the dawn of time. Life, at least in chemical possibility, could have had a longer runway than we assumed. That is another layer of extremity. The universe may not only be larger in structure, but richer in opportunity. And if multiverse models are correct, then somewhere beyond our horizon, other universes may host entirely different evolutionary arcs, some sterile, some vibrant, some governed by physics we would barely recognize. We cannot travel there. We cannot communicate. But we can ask whether their birth influenced ours. That question alone stretches the human frame to its limit, because it reframes isolation. We are not asking whether we are alone among stars. We are asking whether our universe itself is alone. JWST does not answer that. Not yet. But it forces the question into observational territory, and that is enough to shift our sense of place. We are small, but we are positioned at a moment where the first light of the cosmos is no longer myth. It is data. And that data is hinting that the beginning may have been more interconnected, more dynamic, more extreme than the clean diagrams in textbooks suggest. Somewhere in those early hundreds of millions of years, something accelerated. Whether it was the raw efficiency of gravity in a denser universe, the furious birth and death of massive primordial stars, a subtle modification of dark matter behavior, or the faint imprint of a neighboring cosmic bubble. The early universe did not wait. It surged. And now, 13.8 billion years later, we are finally catching up to that surge. Catching up means running toward the beginning. Not metaphorically, physically. Every time JWST locks onto a faint red smudge at the edge of detectability, it is intercepting light that has been racing toward us since the universe was barely awake. That light has crossed expanding space for more than 13 billion years. It has outlived stars, galaxies, even entire galactic collisions, and only now does it end its journey in a detector cooled to a few degrees above absolute zero. We intercept it. We decode it. And what it shows us is a universe that refused to grow slowly. To feel how extreme that is, compress time again. If the universe's 13.8 billion years were a single 24-hour day, then the first 500 million years would pass in just 52 minutes after midnight. By 12:52 a.m., some of these galaxies already look surprisingly mature. Before sunrise on this cosmic day, structures the size of the Milky Way may already be assembling. That pace bends intuition. Because we are creatures of gradualism, mountains erode over millions of years, evolution crawls across epochs, civilizations rise over centuries. But the early cosmos may have behaved more like a detonation than a drift, and detonations amplify whatever irregularities exist. Let's descend into that first billion years. Dark matter halos collapse first. They form gravitational wells deep enough to trap gas. Gas falls inward, heats, compresses, and ignites nuclear fusion in the first stars. Those stars are enormous, perhaps 100 to 300 times the mass of our Sun. They burn through their fuel in a few million years and explode. Each explosion is not just a death, it is an upgrade. Heavier elements allow gas to cool more efficiently. Cooling allows clouds to fragment. Fragmentation allows more stars to form. This positive feedback loop can snowball. If the initial density fluctuations were slightly stronger than we estimated, the snowball becomes an avalanche. And avalanches do not wait politely for our models to catch up. But here is where the idea of another universe regains its tension. Because initial fluctuations are not random noise in most inflationary theories, they are quantum fluctuations stretched to cosmic scale. Quantum fluctuations are unpredictable in detail, but predictable in statistics. The cosmic microwave background confirms those statistics with astonishing precision. If JWST's galaxies truly require fluctuations stronger than those statistics allow, then something outside the standard inflationary picture may be necessary. That something does not automatically mean a neighbouring universe, but it reopens the door. Inflationary multiverse models suggest that each bubble universe emerges with its own realization of quantum fluctuations. Most look statistically similar, but rare interactions, collisions, could inject anomalies. What would a collision look like? Not two universes smashing like billiard balls, more like overlapping pressure waves in space-time. At the boundary, energy density spikes, fields oscillate, the geometry of space warps slightly. Once inflation ends, that distortion freezes into the newborn universe as a region with altered condition. Over billions of years, that region evolves differently. To us, it might appear as an unexpected cluster of early massive galaxies, not because stars crossed over. Now hold that thought against another possibility. Perhaps the tension lies not in the beginning, but in our interpretation of light. Estimating stellar mass at extreme redshift is difficult. We rely on models of stellar populations, assumptions about dust, about star formation histories. A small error in assumptions can inflate mass estimates. Some early JWST galaxies, initially thought to rival the Milky Way, have since been revised downward after spectroscopic confirmation. Science breathes. It overestimates. It corrects. It refines. But even revised masses remain impressive. Even conservative numbers suggest galaxies forming stars at rates far exceeding expectations for such an early epoch. And that forces adaptation. Simulations are being updated with more aggressive star formation prescriptions. Dark matter models are being tested for subtle interactions. Feedback mechanisms are being recalibrated. The universe is not obligated to match our first draft. But here is the emotional pivot. Whether the explanation is internal revision or external influence, the implication is the same. The early universe was not simple. We like clean origin stories, a smooth expansion, gradual clumping, predictable growth. Instead, we are confronting a beginning that may have been jagged, interconnected. And if eternal inflation is correct, then our observable universe is just a patch, a luminous island in a vast, inflating ocean. Beyond our cosmic horizon, expansion outpaces light. We will never see those regions directly. But the earliest instance, when distances were microscopic, may have allowed interactions before horizons diverged. That is the only window where universes could leave fingerprints on one another. A window smaller than a proton, earlier than a trillionth of a second, and yet capable of shaping galaxies billions of years later. This is the scale of causality we are playing with. You, me. Atoms forged in stars, living on a planet around a star in a galaxy that may owe its rapid assembly to fluctuations seeded at a boundary between inflating space-time regions. It sounds mythic, but it is built from equations and from photons. If JWST ultimately shows that ordinary physics, pushed harder, explains everything, that is not a disappointment. It would mean gravity is more potent under early conditions than we imagined. It would mean the cosmos is self-sufficient in its extremity. But if subtle inconsistencies persist, if patterns emerge across larger surveys, suggesting directional asymmetry in early structure formation, then cosmology will face a profound choice. Expand the model within one universe, or expand the number of universes. Either path enlarges reality. And here is the quiet human truth beneath all of it. We are the first species on this planet capable of asking whether our universe has neighbours. For billions of years, galaxies formed, merged, evolved, without witnesses. Now, on a small world orbiting an ordinary star, intelligence has emerged that can reconstruct events from 13 billion years ago and question whether those events were influenced by domains beyond observable space. That is not insignificance. That is participation. We are not central, but we are conscious. And consciousness looking backward across time is one of the rarest phenomena the universe has produced, at least in this region. JWST is still young. Its mission will continue. Deeper fields will be observed. Spectra will sharpen. Statistical samples will grow. The story is not finished. Scientists are still uncovering how the earliest galaxies assembled, how quickly heavy elements spread, how dark matter behaved under primordial conditions. The multiverse remains a frontier, possible within theory, unconfirmed in observation. But the fact that we can even place it on the table of serious discussion marks a threshold in human thought. Once, the Milky Way was the universe. Then it was one galaxy among billions. Now, even our entire observable universe may be one region among many. Each expansion of scale has felt destabilizing. Each has ultimately enlarged our sense of wonder. And that is where we stand now, on a planet that did not exist when the light we are studying began its journey, holding instruments that can read that light, facing data that suggests the dawn was more explosive than we imagined, possibly influenced by events beyond our cosmic horizon. The early universe surged, and whether that surge was entirely our own or brushed by another reality, its consequences are written across the sky. We are still decoding the script. But one thing is clear. The beginning was not quiet. It was immense. And it may have been larger than a single universe. Larger than a single universe is not just a poetic stretch. It is a mathematical possibility that refuses to disappear. Because inflation, the theory that best explains why the universe looks so uniform and flat on large scales, does something unsettling when you let it run all the way through its own logic. It does not stop cleanly. In many versions of inflation, space expands exponentially because of a high-energy field. That field decays in patches. Where it decays, inflation ends, and a hot Big Bang begins. That patch becomes a universe like ours. But elsewhere, inflation continues. Forever. This is not exaggeration. It is called eternal inflation. If true, our universe is not the event. It is an event. a localized transition in a much larger inflating background. Now pause and feel that scale. The observable universe contains roughly 2 trillion galaxies. Each galaxy contains billions to trillions of stars. Around many of those stars orbit planets. On at least one of those planets, consciousness has emerged. And yet all of that may be just one bubble in an endlessly expanding cosmic foam. When JWST looks toward the earliest light, it is peering toward the epoch when our bubble was newly formed, when inflation had just ended here. That boundary between inflating space and hot Big Bang conditions is not just a temporal transition. It is a physical one. Energy locked in the inflation field converts into particles. Radiation floods space. Matter begins to assemble. If another bubble formed nearby in that primordial era, its boundary could have interacted with ours before the two were ripped apart by further expansion. The key word is before, because once space inflates sufficiently, distances grow faster than light can bridge. After that, separation becomes permanent. So any evidence of interaction must be fossilized in the earliest conditions. This is why the first few 100 million years matter so much. They are close, cosmically speaking, to the transition out of inflation. If something unusual happened at that boundary, it would influence the initial density field, and the density field determines where galaxies form. This is not mysticism. It is causality stretched to its limit. Think of ripples on a pond. If 2 stones are dropped close together, their waves intersect. Where the waves reinforce each other, peaks grow higher. Where they cancel, troughs deepen. Translate that to space-time at the birth of a universe. If 2 inflationary regions interacted, the energy fluctuations at the interface could amplify certain modes of density variation. Those amplified regions would collapse into galaxies sooner. They would shine earlier. They would look too mature for their age. JWST may be detecting exactly that kind of amplification. Or it may simply be revealing that our baseline expectations were too conservative. Both possibilities are profound, because either the universe is internally more extreme than we modelled, or its origin story includes external influence. There is another angle to consider, the cosmological principle. For decades, cosmology has operated under the assumption that the universe is homogeneous and isotropic on large scales, that it looks roughly the same in every direction. Observations largely confirm this, but roughly leaves room. Subtle anomalies have appeared in large-scale surveys, unexpected alignments, temperature asymmetries in the cosmic microwave background, statistical quirks. Most are explainable within standard models. Some remain debated. If early massive galaxies cluster unevenly across the sky, that could challenge perfect isotropy. JWST's field of view is still limited. It has not yet mapped the entire early universe. But as surveys expand, patterns may emerge. Patterns are dangerous. If early galaxy formation shows directional dependence, if one region of the sky appears systematically more evolved at the same redshift than another, that would be difficult to reconcile with simple random fluctuations. It would suggest initial conditions that were not entirely uniform, and initial conditions are fingerprints of origin. Yet caution is necessary. The universe has surprised us before without requiring extra universes. Dark energy, discovered in 1998, revealed that cosmic expansion is accelerating. That was shocking, but it did not require abandoning the single universe framework. Black holes were once theoretical oddities. Now we have imaged one. Time and again, extremity has turned out to be a natural feature of our cosmos rather than evidence of something beyond it. So where does that leave us? In tension. And tension is productive. The early JWST results triggered headlines suggesting galaxies that should not exist. That language is dramatic, but underneath it lies careful analysis. Mass estimates depend on stellar population models. Redshifts must be spectroscopically confirmed. Dust can mimic older stellar populations. Active galactic nuclei can boost brightness. As more data arrives, some anomalies shrink, others persist. This is the rhythm of frontier science. You push your instruments to their limit. You encounter something unexpected. You test whether the unexpected is an illusion. If it survives scrutiny, you rewrite theory. If it dissolves, you refine technique. Right now, we are in the middle of that process. And the multiverse remains a possibility, not because we want it to be, but because inflationary mathematics allows it. There is something psychologically destabilizing about them. We already endured the loss of centrality when Earth was displaced from the center of the cosmos. Then the Sun was demoted to one star among billions. Then the Milky Way became one galaxy among trillions. Now, even our universe may be one bubble among countless others. Each step has reduced our physical centrality, but each step has expanded our conceptual reach. We may not be central, but we are capable of understanding structures vastly larger than ourselves. That is a different kind of significance. If the farthest galaxies JWST sees are entirely products of our universe's internal physics, then we are witnessing the raw power of gravity and primordial gas at its most efficient. If they carry subtle signatures of inflationary boundary effects, then we are glimpsing the edge of a multiverse. Either way, the message is the same. Reality is larger than we assumed even a decade ago. And here is the final layer of scale. No matter how large the multiverse might be, no matter how many bubble universes inflate beyond our horizon, our observable region is finite. There is a limit to what light can ever bring us. Even if other universes exist, we may never confirm them directly, but we do not need to see everything to feel the expansion of possibility, because the act of asking reshapes us. On this planet, thin atmosphere, fragile biosphere, orbiting a mid-sized star, we are decoding events that happened when space-time itself was young. We are questioning whether our universe has neighbours. We are doing it with mirrors, mathematics, and patience. JWST's discoveries are not the final word. They are the opening movement of a deeper investigation. Scientists are still uncovering how the earliest galaxies formed, how inflation ended, how dark matter sculpted structure, and whether any anomalies persist across larger datasets. The frontier is active. The story is unfolding in real time. But one conclusion already stands firm. The early universe was not timid. It ignited, accelerated, assembled. It may have done so entirely on its own, or it may have been nudged by a neighbouring reality at the dawn of existence. We do not yet know which. But we are closer to the beginning than any generation before us. And at that distance, even the possibility that our universe is one among many stops being abstract philosophy and becomes a question written in ancient light. Ancient light is patient. It does not rush. It does not care whether we are ready. It simply travels year after year, billion after billion, stretching as space stretches, cooling as the universe cools, carrying within it a record of conditions that no longer exist. When JWST captures that light, it is not observing objects as they are. It is intercepting messages from a universe that was still assembling itself. And what those messages suggest is not calm infancy, but accelerated growth. Let's push deeper into the physics of that acceleration. In the standard cosmological model, tiny density fluctuations, seeded during inflation, grow under gravity. Dark matter collapses first, forming halos. Baryonic matter, ordinary matter, falls in later. Star formation ignites within those halos. The rate at which structure grows depends on three major ingredients: the amplitude of the initial fluctuations, the behaviour of dark matter, the expansion rate of the universe. If any one of those shifts even slightly, the timeline changes. Now imagine that during inflation, quantum fluctuations were amplified a bit more strongly in certain regions. That amplification would not alter the laws of physics. It would alter the starting map of density. Higher peaks collapse sooner. Sooner collapse means earlier stars. Earlier stars mean earlier heavy elements. Earlier heavy elements mean more efficient cooling and faster galaxy growth. This is a domino chain stretching from fractions of a second after the Big Bang to the galaxies JWST now sees. And here is where the multiverse re-enters, not as spectacle, but as a mechanism. If inflation was eternal and bubble universes formed through quantum tunneling events in the inflation field, then collisions between bubbles are possible in principle. Simulations of such collisions suggest they would leave imprints, circular or elliptical temperature anomalies in the cosmic microwave background, or gradients in density across large scales. Those imprints would be subtle, not catastrophic, because by the time galaxies formed, billions of years had passed. Any primordial disturbance would be diluted by expansion and evolution. But subtle does not mean undetectable. It means we must look carefully. JWST is not designed to map the entire sky, but it can probe specific deep regions with extraordinary sensitivity. If the earliest galaxies show unexpected clustering, or systematically higher masses than allowed by Gaussian fluctuations predicted by simple inflation, that would be a clue, not proof. A clue. The distinction matters, because extraordinary claims demand extraordinary evidence. And cosmology moves slowly when it comes to rewriting its foundation. Because for the first time in history, we are not merely speculating about other universes from philosophical grounds. We are confronting observational puzzles that force us to test whether our universe's early conditions were entirely self-contained. That is new. That is destabilizing. And that is thrilling. Now zoom out further. Even if no multiverse interaction occurred, the early universe was operating under extreme conditions we rarely experience today. Matter density was millions of times higher than now. Radiation pressure was significant. Black holes formed rapidly from collapsing massive stars. Some of those black holes grew into supermassive black holes astonishingly fast. JWST has also detected quasars, bright accreting black holes, at redshifts above 7. That means supermassive black holes weighing hundreds of millions of solar masses existed when the universe was less than 1 billion years old. How do black holes grow that quickly? Accretion is limited by radiation pressure, the Eddington limit. Exceed it too much, and radiation blows material away. Yet, early quasars suggest black holes reached enormous masses rapidly. Again, either growth was more efficient than expected, or initial conditions were more extreme. Notice the pattern. Over and over, the early universe appears impatient. Galaxies too big, stars forming too fast, black holes too massive. It is as if gravity in its youth operated with urgency. That urgency does not violate physics, but it stretches our comfort zone. And stretching comfort zones is where cosmology evolves. If multiverse models are wrong, inflation still likely occurred. The evidence for a rapid exponential expansion early in cosmic history is strong, but inflation itself raises philosophical weight. If inflation happened once, what stops it from happening repeatedly in different regions? Nothing in the simplest equations forbids it, which means our universe might not be unique, not in existence, not in structure, perhaps not even in the emergence of life. Some bubble universes might collapse immediately, others might expand too quickly for galaxies to form, some might have physical constants that prevent chemistry. But in a sufficiently vast multiverse, even rare conditions become inevitable somewhere. And that reframes rarity. We often ask, what are the odds that the constants of physics allow life? In a single universe framework, that question feels sharp. In a multiverse framework, it softens. We exist in a region where conditions permit observers, because observers can only arise there. That reasoning is called anthropic selection. It is controversial. It is uncomfortable. But it is logically consistent. And JWST's glimpse into early structure formation nudges us closer to asking whether our cosmic history is one draw among many. Still, restraint is necessary, because every anomaly does not demand a multiverse. Many tensions in cosmology resolve with improved modelling. Already, some early JWST galaxy masses have been reduced as better spectral data arrives. Dust obscuration complicates interpretation. Active starburst regions can mimic older stellar populations. The frontier is noisy. But noise is not emptiness. It is information waiting to be filtered. Here is what we know with certainty. The universe formed structure remarkably quickly. Within a few 100 million years, galaxies were already assembling at significant scale. Within a billion years, supermassive black holes existed. Within a few billion years, mature galactic ecosystems flourished. And eventually, on at least one planet, life emerged capable of looking back. That arc is not speculative. It is observable. What remains uncertain is whether that arc was influenced by conditions beyond our observable boundary. Scientists are still uncovering whether early density fluctuations align perfectly with simple inflationary predictions or hint at additional processes. Future missions, next-generation space telescopes, 21-centimeter hydrogen surveys mapping cosmic dawn, improved cosmic microwave background measurements will refine the picture. The coming decades will sharpen this question. But regardless of outcome, something fundamental has shifted. We no longer see the Big Bang as a clean, singular beginning. We see it as a phase transition, possibly one among many. We no longer see early galaxies as tentative sparks. We see them as blazing engines of rapid assembly. We no longer treat the multiverse as purely metaphysical. We treat it as a hypothesis anchored to inflationary theory and now brushed by observational tension. And here is the quiet, human-scale truth inside all this enormity. We are alive at the moment when the first generation to directly observe cosmic dawn is asking whether dawn itself was shaped by neighbouring realities. We are small, but we are present, and presence matters. Because ancient light travelled for billions of years without witness? Until now. Now it lands in detectors. Now it becomes data. Now it becomes questions. And whether those questions ultimately reveal a universe more efficient than expected, or a cosmos larger than singularity, the outcome is the same. Reality is deeper than we imagined. The beginning was faster than we thought, and the edge of the observable universe may not be a wall, but a horizon beyond which possibility continues. A horizon is not an ending. It is a limit of sight. Stand on a shoreline and the ocean appears to stop at a clean blue line. Walk forward and that line retreats. The edge was never a boundary of existence, only a boundary of perspective. The observable universe works the same way. There is a radius beyond which light has not had enough time to reach us. That radius is not the edge of reality. It is the edge of what we can currently see. Beyond it, space continues. And if inflation is correct, beyond it, space may not just continue, it may branch. So when JWST stares into the deepest dark, it is not looking at the whole universe. It is looking toward the thinning fog of cosmic infancy, close to the limit of visible history. And near limits, small deviations matter more, because there is less time for complexity to accumulate. If you see a skyscraper 5 minutes after sunrise, you question the construction timeline. If you see a skyscraper in a city that has existed for centuries, you do not. JWST is seeing skyscrapers in the first minutes of the cosmic morning. Now imagine that we eventually confirm, beyond dispute, that early galaxies formed faster than any conventional simulation predicted, even after accounting for dust, feedback, and dark matter refinements. Imagine that directional asymmetries appear, subtle but persistent, suggesting that one region of the early universe evolved differently from another. At that point, cosmology would confront a choice not of imagination, but of consistency. Do we modify gravity at high energies? Do we introduce new particle physics in the primordial plasma? Or do we accept that our bubble's earliest boundary conditions were influenced by something beyond it? None of those paths are trivial. All would reshape textbooks. But here is the deeper shift already underway. We are no longer asking whether the universe is big. We are asking whether it is singular. That question changes scale from spatial to ontological. For centuries, infinity meant endless space. Now infinity may mean endless realities. And if that is true, then what we call the beginning might be local, a phase change in one region of a far larger inflating expanse. It was the birth of our everything. That distinction is seismic, because it transforms the Big Bang from absolute origin into regional event. Yet even in that framework, our universe remains self-contained in practice. The speed of light and accelerating expansion ensure that if other universes exist, they are forever causally disconnected from us. We cannot travel there. We cannot receive messages. We cannot send probes. Any evidence must be fossilized in the earliest measurable conditions, and that is why JWST's discoveries feel electric. They brush the only accessible layer where such fossils could survive. But even if no multiverse interaction ever occurred, even if inflation was a one-time event, the implications of JWST's early galaxies remain immense, because they reveal that structure formation in our universe was more dynamic, more aggressive, more efficient than we allowed. That alone deepens the story. It suggests that cosmic dawn was not a dim flicker. It was a blaze. And that blaze seeded everything that followed. Every spiral galaxy, every cluster, every planet, every ocean, every cell, every thought. The speed of early assembly affects chemical evolution timelines. If heavy elements formed sooner, planetary systems could have emerged earlier. If planetary systems emerged earlier, the window for life widens. The universe may have had more time, not less, for complexity to unfold. That reframes our own emergence. We often think of ourselves as late arrivals in a slow cosmic evolution, but perhaps we are a product of a universe that sprinted early and coasted later. Perhaps the intense acceleration of structure in the first billion years laid the groundwork for long-term stability. Gravity built fast. Then time refined. And in that refinement, consciousness arose. Now consider the emotional symmetry of this moment. The earliest fluctuations of space-time, possibly influenced by inflationary dynamics beyond our horizon, may have set the conditions for galaxies to assemble rapidly. Billions of years later, inside one of those galaxies, beings evolved who can contemplate whether their cosmic origin was singular or plural. The beginning may have been shaped by unseen boundaries. The present is shaped by awareness. We are downstream of ancient physics, but we are also upstream of interpretation. That matters. Because the universe does not ask whether it is alone. We do. JWST will continue its mission. It will peer deeper. It will refine redshifts. It will confirm or revise mass estimates. Future observatories will map the 21-centimeter hydrogen signal from the cosmic dawn, revealing when the first stars ionized the intergalactic medium. Cosmic microwave background experiments will tighten constraints on inflationary parameters. Large-scale surveys will test isotropy with greater precision. Piece by piece, the puzzle will sharpen. The multiverse may remain theoretical, or subtle anomalies may accumulate into persuasive evidence that our early boundary conditions were not entirely self-contained. But no matter how the data resolves, one truth is already clear. The universe we inhabit is not simple. It did not unfold timidly. It expanded violently. It formed structure rapidly. It produced extremes early. And it continues to surprise us. Stand beneath the night sky. Every star you see is inside the Milky Way. Every galaxy beyond is invisible to the naked eye. Yet trillions exist. Now extend that thought. Every galaxy we can ever observe is inside our observable universe. Beyond that horizon may lie more galaxies, and beyond those, perhaps other universes entirely. We may never cross that final boundary, but we have reached the point where we can detect hints written into ancient light. Hints that the cosmic dawn was more intense than expected. Hints that the beginning might not have been solitary. And even if the ultimate answer remains subtle, the act of reaching this far changes us. Because we are no longer confined to myths about the sky. We are interrogating the birth of reality itself. We are measuring photons older than Earth. We are testing whether our universe has neighbours. And whether the answer is yes or no, the scale of the question alone expands our sense of existence. We are small, but we are awake at the edge of the observable. We are listening to the oldest light, and that light is telling us that the beginning was vast, perhaps even vaster than a single universe. And here is the quiet twist in all of this. Even if we never confirm another universe, The mere fact that our equations allow it means reality is already bigger than our instincts were built to handle. Because our instincts evolved on a savanna. They evolved to judge distance by footsteps, time by seasons, danger by movement in tall grass. They were never meant to pass 13.8 billion years. They were never meant to contemplate inflation fields fluctuating in fractions of a second. And they were certainly never meant to hold the possibility that existence might be one bubble among countless others. Yet here we are. A biological species stitched together from atoms forged in early stars, using mathematics to reverse engineer the first moments of space-time. JWST did not invent the multiverse, but it has intensified the pressure on our earliest timeline. And pressure is how new understanding forms. Let's return to the galaxies themselves. When JWST images a galaxy at redshift 12 or 13, we are seeing light emitted roughly 300 to 400 million years after the Big Bang. That is extremely early. At that time, the universe was still emerging from the cosmic dark ages, when neutral hydrogen filled space and no stars had yet ignited. Then came reionization, the epoch when the first stars and galaxies produced enough ultraviolet radiation to strip electrons from hydrogen atoms, transforming the intergalactic medium. JWST is peering into that transition, and it is finding not just faint proto-galaxies, but systems that appear structurally complex. Some show disk-like features. Some show signs of mergers. This suggests that hierarchical assembly, small structures merging into larger ones, was already underway, which means gravitational collapse had momentum. Now imagine overlaying that with a slight primordial asymmetry, perhaps seeded by inflationary boundary effects. A region with marginally higher density contrast would enter this collapse phase sooner. Its galaxies would lead the cosmic timeline. From our vantage point, billions of years later, we would detect that leadership as anomaly, but it would simply be the echo of a head start. And here is the most powerful part. A head start of even 1% in initial density can translate into enormous structural differences after hundreds of millions of years of gravitational amplification. Gravity is patient but relentless. Small advantages compound. In finance, compounding interest grows wealth exponentially. So the question becomes razor sharp. Were the initial fluctuations in our observable patch exactly what simple inflation predicts? Or were they ever so slightly skewed? Cosmic microwave background measurements show extraordinary agreement with simple models. But JWST is probing structure formation hundreds of millions of years later. Different scales, different regimes. It is possible that both datasets are consistent with a single universe inflation model. It is also possible that subtle deviations only emerge when we combine them. This is how science moves at the frontier, not through dramatic declarations, through tightening constraints, through reducing error bars, through letting anomalies either dissolve or sharpen. Right now, they are sharpening just enough to keep the question alive. And the emotional gravity of that question is enormous. Because if our universe is one bubble among many, then the totality of existence is not a single expanding space-time, but an ensemble. An ensemble where physical constants may vary. An ensemble where some universes expand too fast for structure. Some collapse too quickly. Some never form atoms. Some never cool. Some may host entirely unfamiliar forms of matter. And ours, this one, happens to support galaxies, stars, planets, chemistry, life. That does not diminish us. It reframes us. Instead of being the center of everything, we become a local success in a vast cosmic landscape. But notice something crucial. Even if the multiverse exists, it does not reduce the beauty or extremity of our universe. Because this universe is still 93 billion light-years across in observable diameter, it still contains trillions of galaxies. It still produced black holes with masses billions of times that of the Sun. It still accelerated its own expansion through dark energy. It still forged consciousness from star debris. The multiverse, if real, expands the stage. It does not shrink the drama. And if the multiverse turns out to be unnecessary, If improved models of star formation and dark matter fully explain JWST's early galaxies, then we are left with something equally astonishing. A universe so efficient, so violently productive in its infancy, that it assembled immense structures almost immediately after birth. That is not a modest cosmos. That is a cosmos that surged. In both cases, multiverse or not, the early universe refuses to be dull. It demands revision. It demands imagination tethered to data. And it demands humility. Because we are interpreting the faintest signals imaginable. Infrared photons that have crossed billions of light years. Spectral lines barely distinguishable from noise. Statistical deviations that require entire teams to validate. And from that fragility of signal, we are extracting questions about the totality of reality. That is the paradox. The biggest questions arise from the smallest measurements. Now slow down. Step back. Look at the arc. From a hot, dense state 13.8 billion years ago, to density ripples stretched by inflation, to gravitational collapse, to the first stars igniting, to galaxies assembling with surprising speed, to heavy elements seeding planets, to life emerging, to intelligence building telescopes, to that intelligence asking whether its universe has neighbours. That arc is real. That arc is measurable. And whether the early galaxies JWST spotted ultimately reveal exotic boundary interactions or simply force us to update our models of cosmic dawn, one truth remains untouched. We are living at the moment when the beginning of everything we know is finally coming into focus. The farthest galaxies are not just distant objects. They are time capsules from the edge of origin. And as we open them, we are discovering that the dawn of our universe may have been faster, brighter, and possibly more interconnected than we ever imagined. Small planet, ordinary star, edge of a spiral galaxy. Yet from here, we are interrogating the birth conditions of reality itself. We may never cross the cosmic horizon, but we have reached it with our eyes. And at that boundary, the universe does not feel smaller. It feels infinite in possibility, whether singular or one among many. And here is the final shift, the one that lingers after the data tables close and the simulations finish running. Even if the multiverse remains unconfirmed, even if every early JWST galaxy eventually fits inside refined models of star formation and dark matter, the psychological boundary has already moved. Because we have crossed a threshold. For the first time in human history, we are not just mapping the structure of the universe. We are interrogating its birth conditions with instruments precise enough to expose tension. That is new. That is irreversible. Think about the escalation of scale across human history. First, the sky was a dome. Then it was a sphere of stars. Then it was a galaxy. Then billions of galaxies. Then cosmic expansion. Then dark energy. Now, possibly multiple universes. Each step felt absurd before it felt obvious. Each step destabilized intuition. Each step eventually became the new baseline. So what happens if, decades from now, evidence accumulates, subtle anisotropies, statistical deviations, inflationary signatures, that strongly suggest our observable universe carries the imprint of a boundary interaction? What happens if cosmologists converge on the conclusion that inflation did not happen once, but continuously, and we are in one pocket among many? The night sky will not change. The stars will not rearrange. Gravity will not weaken. But our definition of everything will. Everything will no longer mean all that exists. It will mean all that exists here. That distinction is profound, because it moves us from a universe-centered worldview to a locality-centered one. We would become residents of a region, not occupants of totality. And yet, here is the paradox. Our region would still be unimaginably vast. Even as one bubble, our observable universe contains more stars than there are grains of sand on Earth. Even as one patch, it spans distances so large that light takes billions of years to cross it. Even as one instance, it is sufficient to generate complexity, chemistry, biology, and awareness. The multiverse, if real, does not diminish that. It multiplies it. Now consider the alternative ending. Suppose future observations show that early galaxy formation can be fully explained by more efficient starburst activity, revised stellar population models, and subtle shifts in dark matter collapse dynamics. Suppose every anomaly resolves within the single universe framework. What then? Then we will have discovered that our universe is more extreme than we imagined. That gravity in the dense early cosmos was astonishingly productive. That structure formation was not hesitant, but explosive. That supermassive black holes can assemble with startling speed. That chemical complexity arrived earlier. That the conditions for planets and possibly life emerged sooner than expected. In that case, the story becomes no less epic. It becomes a story of internal ferocity rather than external interaction. Either way, neighbouring universes or not, the early cosmos was not timid. It surged. And we are only now catching up to that surge with our instruments. Pause here. Look up tonight. The stars you see are local. The galaxies JWST sees are ancient. Beyond them lies darkness, not because nothing exists, but because light has not yet had time to arrive. And beyond that horizon may lie more of our universe. And beyond that, perhaps others. We may never confirm what lies past the ultimate boundary. But we have already expanded our conceptual map far beyond what evolution prepared us for. We are organisms built from carbon, oxygen, nitrogen, elements forged in early stars. Those stars formed in galaxies. Those galaxies formed from primordial density ripples. Those ripples may have been shaped by inflation, and inflation may have occurred in a landscape larger than our own cosmic bubble. Trace that chain carefully. Every breath you take may be downstream of quantum fluctuations amplified in the first fraction of a second of cosmic history, and those fluctuations might not have been entirely isolated. It is a possibility, not a conclusion, but a possibility powerful enough to alter how we frame existence. The most extraordinary part is not that other universes might exist. It is that a species on a small rocky world has reached the point where that question can be approached scientifically. We are not speculating from ignorance. We are probing from data. Future telescopes, larger mirrors, colder detectors, deeper surveys will push closer to the cosmic dawn. Gravitational wave observatories may one day detect primordial signals from inflation itself. Cosmic microwave background experiments will refine measurements of polarization patterns, searching for the fingerprints of high-energy physics in the earliest light. Each improvement narrows the gap between imagination and measurement, and somewhere in that narrowing, the truth will crystallize. Maybe the universe is singular but more dynamic than we thought. Maybe the farthest galaxies JWST spotted are simply the universe flexing its early strength. Or maybe they are faint echoes of something even larger, brushing against our cosmic infancy. We do not yet know. Scientists are still uncovering the details, refining the numbers, testing the boundaries. But uncertainty here is not emptiness. It is frontier. And frontier is where attention belongs. Now slow the pace. Zoom out completely. 13.8 billion years. Trillions of galaxies. Unimaginable distances. Possible neighbouring universes. And here, on a planet orbiting an ordinary star, a species capable of asking whether its universe is alone. We are small in scale, but we are immense in perspective. The farthest galaxies JWST has seen are not just distant lights. They are mirrors reflecting how far thought itself has travelled, from campfires under ancient skies, to mirrors of gold unfolding in deep space, to the edge of the observable universe, to the edge of the possible multiverse. Whatever the final answer becomes, one truth is already secure. Reality is larger than our instincts. The beginning was faster than our models predicted, and the horizon we once thought was absolute is now just another line waiting to be crossed. small, included, awake at the edge of everything we can see, and listening to the oldest light in existence, as it tells us that the story may be bigger than a single universe. And now, at the farthest reach of vision, we arrive at something unexpected, not a wall, not a final answer, but a widening silence. Because here is the deepest truth hidden inside all of this. The observable universe is finite, not small, not remotely small, but finite. There is a limit to how far light has travelled since the beginning, a limit to how much history can physically arrive here, a boundary written not in stone, but in time. Beyond that boundary, space continues. And if inflation is correct, beyond that continuation may exist regions that will forever remain unreachable. Not because we lack technology, not because we lack courage, but because space-time itself forbids the crossing. That is the ultimate scale of this question. Even if other universes exist, even if bubble after bubble inflates beyond our horizon, even if reality is a vast cosmic foam, there is a permanent causal separation. We are inside our patch. And yet, inside this patch, something extraordinary happened. Structure formed. Stars ignited. Heavy elements spread. Planets condensed. Chemistry experimented. Life emerged. Consciousness woke up. And consciousness built a telescope that can see nearly back to the beginning. That is not trivial. That is the universe folding back on itself. JWST is not just an instrument. It is a feedback loop. Matter observing its own origin. Light emitted in the first few 100 million years now striking detectors engineered by descendants of that same early matter. That symmetry is staggering. And it reframes the multiverse question. Because whether or not other universes exist, this one produced observers capable of contemplating the possibility. That fact alone is rare, at least in our experience. We do not yet know how common life is. We do not, but we know it happened here. And we know it happened in a universe that formed galaxies astonishingly fast. So here is the final emotional inversion. The early galaxies JWST spotted may or may not be evidence of another universe's influence. But they are unquestionably evidence of this universe's creative intensity. It was ambitious. It built large. It built fast. It seeded complexity early. And in doing so, it laid the groundwork for everything that followed. If there are other universes, they may have their own dawns, their own accelerations, their own pathways to structure. Some may remain forever dark. Some may burn too briefly. Some may never assemble atoms. But ours did. Ours assembled stars within a few 100 million years. Ours assembled black holes that grew monstrous before the universe reached 1 billion years old. Ours assembled galaxies dense enough to surprise our best simulations. Ours assembled a planet where oceans formed, continents drifted, life diversified, and intelligence eventually looked back across 13 billion years and asked, was this singular? That question does not shrink us. It elevates us. Because asking it means we have reached the boundary of the observable and pressed against it with mathematics and light. We may never step beyond the cosmic horizon, but we have touched it. We have traced it. We have measured its curvature and timed its expansion. We have found galaxies near its edge that challenge our expectations. And in doing so, we have expanded our internal horizon, even if the external one remains fixed. The multiverse, if real, does not make our universe less meaningful. It makes existence more abundant. And if the multiverse is not real, if our universe is the whole story, then this single universe is more extraordinary than we dared to imagine. Either way, the outcome converges. Reality is vast beyond instinct. The beginning was violent beyond comfort. The early cosmos surged beyond prediction. And from that surge came us. Not central, not dominant, but aware. Aware enough to build mirrors that unfold in deep space. aware enough to decode photons that began travelling before Earth existed, aware enough to confront the possibility that our universe might have neighbours, and aware enough to feel the weight of that possibility without collapsing under it. Now zoom out one final time. A universe, or perhaps many universes, expanding. Galaxies forming in the first flicker of cosmic time. Black holes igniting like gravitational engines. Stars forging the atoms of life. A small planet forming in the spiral arm of one galaxy. Life evolving. Consciousness emerging. A telescope lifting its gaze. Ancient light arriving. Questions igniting. This is not a story of isolation. It is a story of connection across time. Connection between the first quantum fluctuations and the thoughts forming in your mind right now. Connection between cosmic dawn and human curiosity. Connection between the edge of observable space and a species that refuses to stop asking what lies beyond it. We may never confirm another universe, but we have already confirmed something equally profound. The universe we inhabit is capable of producing questions as vast as itself. And that means the story, singular or plural, is already immense. We stand small, but we stand included, at the horizon of light, listening to the oldest photons in existence, and discovering that the beginning was not the end of mystery. It was the opening of something larger than a single universe. And yet, even after all of that, there is one more layer to see. Because when we talk about another universe, we instinctively imagine distance, farther than far, beyond the edge. Somewhere, out there. But inflation does something stranger than distance. It makes separation geometric, not spatial. Another universe, if it exists, is not necessarily sitting beyond a wall of darkness like another island across an ocean. It could be separated by an expansion of space so extreme that no signal could ever traverse it. Not meters apart. Not light years apart. But causally apart. Which means this. The multiverse, if real, is not a place we could travel to, even in principle. It is a condition of reality. A larger structure in which our universe is embedded. That reframes the imagination completely, because it means the boundary we are pressing against with JWST is not a door. It is a limit of causation. And that makes the search even more powerful. We are not explorers hoping to cross. We are investigators searching for fingerprints left at the moment of separation. And fingerprints, if they exist, would be faint. Subtle distortions in density. Tiny deviations in early structure formation. Slight asymmetries amplified over billions of years. That is what makes those distant galaxies so important. They are not just objects. They are tests. They are the first large-scale structures close enough to the beginning to still carry memory of how it unfolded. If they diverge in persistent, structured ways, we learn something equally monumental. The beginning of our universe may have brushed against something larger. Either outcome enlarges reality. Either outcome deepens the story. Now consider the human scale once more. We evolved in a universe already 13.8 billion years old. We did not witness the Big Bang. We did not witness the first stars. We did not witness the first galaxies. We are reconstructing those events from light that travelled across nearly all of cosmic history. And that reconstruction is precise enough to question the very boundaries of existence. There is something quietly overwhelming about that, because it means that intelligence, once formed, does not simply adapt to its environment, it interrogates it. It pushes backward through time. It stretches outward toward the horizon. It refuses to stop at what is immediately visible. JWST is a physical manifestation of that refusal. A mirror in space, cold and silent, unfolding far from Earth, just to capture whispers from the first few 100 million years. And those whispers are loud enough to disturb our models, not shatter them. Disturb them. And disturbance is how progress begins. We are not at the end of this story. We are at the beginning of the beginning. Future observations will multiply the sample size of early galaxies. Spectroscopy will sharpen redshift conformations. Simulations will grow more sophisticated, incorporating feedback processes we barely understood a decade ago. Inflationary parameters will tighten. Constraints on non-Gaussian fluctuations will improve. And slowly, the fog around cosmic dawn will thin. But something irreversible has already happened. We now live in a world where the multiverse is not merely fiction, not merely philosophy, but a hypothesis constrained by data. And we now live in a world where the early universe is not assumed to be gentle. It is observed to be extreme. That changes how we think about existence. Because extremity at the beginning means richness later. Rapid structure formation means earlier chemistry. Earlier chemistry means earlier planets. Earlier planets mean longer windows for life. The universe may have had more time to experiment than we once believed. And that possibility radiates outward. Perhaps we are not late arrivals in a slow cosmic process. Perhaps we are part of a universe that sprinted into complexity and has been evolving ever since. Perhaps what feels like a long cosmic delay was actually a furious early ignition followed by gradual refinement. And somewhere in that ignition, in those first amplified ripples of space-time, the seeds were planted, not just for galaxies, but for awareness. Now, take one final perspective shift. If there are countless universes, most will never know they exist among others. Most will never produce observers. Most may expand silently, structureless. But here, in this one, atoms arrange themselves into minds capable of asking whether there are others. That is not trivial noise in a multiverse. That is a rare configuration of matter achieving reflection. And reflection changes everything. Because once a universe becomes aware of itself, even partially, it gains a new dimension. Not physical, experiential. The early galaxies JWST spotted may or may not trace their origins to interactions beyond our cosmic bubble, but they undeniably trace their consequences to us. They are ancestral. They are part of the chain that leads to this moment of contemplation. Their rapid assembly forged heavy elements. Their supernovae seeded future generations of stars. Their mergers shaped galactic ecosystems. Their descendants include the Milky Way. And inside the Milky Way, on a small world orbiting a yellow star, awareness emerged. Awareness that now looks back and asks whether its universe is singular. That is the full circle. From quantum fluctuation, to galaxy, to planet, to mind, to question. Whether there are other universes or not, that arc is extraordinary. Whether our cosmic dawn was nudged by neighbouring bubbles or unfolded entirely within its own laws, the result is the same. We are here, listening to ancient light, standing at the horizon of the observable, feeling the scale stretch beyond instinct, and realising that the beginning of everything we know may have been larger than we once dared to imagine. Not smaller, not simpler, larger, perhaps singular, perhaps one among many, but vast beyond measure either way. Small planet, ordinary star, edge of a galaxy, edge of the observable universe. And yet, inside this narrow window of space-time, a species has reached out with mirrors and mathematics and touched the dawn. Whatever lies beyond the horizon, whatever reality ultimately turns out to be, we are already participants in its unfolding. Small, included, awake. At the boundary of light. At the boundary of light, something subtle happens. Time thickens. Because the farther we look, the younger the universe becomes. The galaxies JWST detects are not ancient in their own moment. They are young, violently young. They exist in a universe still dense, still turbulent, still restructuring itself from primordial chaos. We are not observing the end of things. We are observing adolescence. And adolescence is unstable. Black holes grow too fast. Galaxies collide frequently. Everything is compressed. Everything is accelerated. Now imagine that compression magnified by even a slight shift in initial conditions. A 1% increase in density fluctuation amplitude at 10 to the power of minus 35 seconds after the Big Bang can echo forward into billion solar mass structures within a few 100 million years. That is how sensitive the beginning is. Tiny differences, massive outcomes, which means that if our bubble universe experienced even a subtle interaction with a neighbouring inflating region, the consequences would not be obvious fireworks. They would be statistical biases, an edge in the data, a slight preference for early collapse in certain directions. Close enough to the beginning that compounding hasn't erased the fingerprints. Far enough away that structure has had time to amplify. This is the razor's edge of cosmology. Too early, and we cannot see. Too late, and memory is diluted. Right now, we are staring at the thin slice where the universe's origin story still whispers through its architecture. But here is the emotional inversion that matters most. Even if no multiverse exists, the fact that our universe allows this level of self-examination is itself staggering. Because reality could have been sterile. It could have expanded too quickly for galaxies to form. It could have collapsed back on itself before chemistry stabilized. It could have lacked the forces necessary for atomic structure. Instead, it balanced delicately. Gravity strong enough to clump matter. Electromagnetism stable enough for chemistry. Nuclear forces tuned for stellar fusion. Dark energy weak enough to allow billions of years of structure before accelerating expansion. Whether that balance is unique or one selection among many in a multiverse, the outcome is the same. This universe supports observers, and those observers are now reaching backward into the first 300 million years and asking whether their origin was locally or cosmically contextual. That is the deepest escalation of all. Because the multiverse question is not just about size, it is about origin. Was the Big Bang the singular birth of all space-time? Or was it one ignition event in an eternally inflating landscape? If it was singular, then everything, every galaxy, every atom, every conscious thought descends from one initial event. If it was plural, then our origin is local, nested within something larger. Both are immense. Both are destabilizing. Both stretch the mind beyond evolutionary comfort. JWST did not prove either. But it did something just as important. It forced cosmology to revisit the first chapter with sharper eyes. And that alone reshapes the narrative. Because until recently, the earliest few 100 million years were largely theoretical territory. Simulated, inferred, extrapolated. Now they are observable terrain. And observable terrain can surprise us. Already, JWST has revealed that galaxy formation began earlier than many models predicted. Already, it has shown that star formation rates were higher. Already, it has hinted that black hole growth was more aggressive. These are not small adjustments. They shift the tempo of the entire cosmic symphony. And tempo matters. A faster early tempo means more rapid chemical enrichment. More rapid enrichment means earlier planetary systems. Earlier planetary systems mean more time for biological evolution before cosmic acceleration thins the density of future galaxy formation. In a universe accelerating under dark energy, structure formation will eventually slow. Galaxies will drift apart. Star formation will decline. We live in a middle era, after the furious birth, before the quiet fade. Understanding how furious that birth truly was changes how we see our place in time. If early structure formed faster, then the universe matured quickly. If the universe matured quickly, then we are not late arrivals to a slow cosmos. We are descendants of an explosive beginning. And that beginning may or may not have been isolated. Now step all the way back. Picture the entire observable universe as a glowing sphere of galaxies suspended in expanding space. Beyond it, more space we cannot see. Beyond that, perhaps other inflating regions, each with their own internal histories. And inside this one sphere, on one small planet, Consciousness, asking about the rest. The irony is sharp. If there are infinitely many universes, most will never produce a species capable of asking this question. Yet here, in this one, the question exists. And that makes this region, this bubble, this patch of space-time, extraordinary, regardless of how many others exist. Because awareness is rare even within our own observable cosmos, as far as we know. The farthest galaxies JWST spotted are not just cosmological curiosities. They are part of the chain that led to us. Their early starbursts forged the elements that would later cycle through countless generations of stars. Their mergers shaped the cosmic web. Their black holes influenced galactic evolution. They are ancestral to the Milky Way's lineage, ancestral to the Sun, ancestral to Earth, ancestral to you. So whether they formed purely under our universe's internal physics, or under conditions subtly influenced by something beyond it, they are part of our origin story. And origin stories matter, because they define scale. They define belonging. They define how small we are, and how included. We may never step beyond the cosmic horizon, but we have traced it with light. We may never confirm another universe directly, but we have reached the stage where its existence is not absurd. It is physically plausible. And we are alive at that stage. Alive at the moment when ancient photons arrive and force us to reconsider the architecture of reality. The early universe surged. Galaxies assembled with urgency. Black holes ignited. Stars exploded. Chemistry blossomed. Life emerged. Awareness formed. And now that awareness stands at the edge of observable space, asking whether the beginning belonged only to us. Singular. Or one among many. Whatever the final answer becomes, one truth is secure. The story is larger than instinct. The beginning was more violent than comfort. And this small planet, orbiting an ordinary star, is not outside that story. It is a continuation of it. Small, finite, but awake. At the edge of light, listening, and discovering that the dawn may have been bigger than a single universe. And here, at the quiet edge of everything we can possibly observe, the story does not explode outward, it settles. Because after the escalation, after the galaxies that shouldn't exist yet, after inflation and bubble universes and horizons that can never be crossed, what remains is something more intimate. The universe began very fast, very hot, very dense. In less than a trillionth of a second, space expanded violently. Quantum ripples were stretched across cosmic scales, energy condensed into particles, matter and radiation flooded existence. Within minutes, the first atomic nuclei formed. Within hundreds of thousands of years, atoms captured electrons and light travelled freely. Within a few 100 million years, stars ignited. Within a billion years, galaxies assembled with surprising maturity. And now, 13.8 billion years later, we are measuring that first light and asking whether the beginning was self-contained. Whether those first ripples were influenced by something beyond our patch of space-time. Whether our cosmic dawn was singular or part of something vaster. We do not yet know. Scientists are still uncovering the structure of early galaxies, still refining inflationary models, still searching for subtle imprints in the cosmic microwave background. But here is what we do know. The universe is not fragile in its scale. It is vast beyond comprehension, and yet it is precise enough to encode its own history in light. JWST did not reveal chaos. It revealed structure, unexpectedly early, unexpectedly strong, unexpectedly confident. If that structure arose purely from internal physics, then gravity in a dense young universe is more powerful than we imagined. If that structure was subtly influenced by neighbouring inflationary regions, then our origin story extends beyond our own bubble. In either case, the beginning was immense, and we are not outside that immensity. We are made of it. Every atom in your body was forged in stars that formed because early density ripples collapsed under gravity. Those ripples trace back to inflation. Inflation traces back to the earliest fraction of a second. And that earliest fraction of a second may connect to a landscape larger than our observable universe. You are not separate from that chain. You are its continuation. The farthest galaxies JWST has seen are not just distant. They are ancestral. They are part of the lineage that leads here. And whether their rapid maturity reflects extraordinary internal efficiency, or the faint echo of another universe brushing ours at the dawn of time, they expand the frame. They force us to confront scale without shrinking ourselves. Because here is the final inversion. The more vast the cosmos becomes, the more remarkable awareness becomes within it. If there is only one universe, then this is the only stage on which consciousness has emerged, at least as far as we know. If there are countless universes, then consciousness is still rare enough that in this one, it has reached the edge of the observable and is asking about the rest. Either way, this moment matters. This moment on this small planet, where ancient photons are being decoded and the boundary of reality is being questioned. We may never confirm a multiverse. We may never see beyond our cosmic horizon. But we have already done something extraordinary. We have reached the point where the beginning itself is no longer myth. It is data. And that data is rich enough to challenge our assumptions about isolation. Now, zoom out one last time. A universe expanding for 13.8 billion years. Galaxies forming at breathtaking speed. Black holes igniting. Stars forging the elements of life. A small rocky world coalescing in the spiral arm of a galaxy. Life rising from chemistry. Consciousness emerging from life. That consciousness building instruments. Those instruments capturing ancient light. That light revealing that the dawn may have been faster, brighter, and possibly more connected than expected. Small, finite, inside a horizon we cannot cross. And yet, awake. Aware of scale. Aware of possibility. Whether singular or one among many, the universe we inhabit is not ordinary. It ignited with violence. It built with urgency. It carried its early history across billions of years so that it could be read. And now it is being read. Not by gods. Not by distant watchers. But by matter that learned how to ask questions. That is the quiet triumph hidden inside the extremity. The farthest galaxies JWST spotted may or may not belong solely to our universe's untouched history, but they undeniably belong to ours. To our story. To this moment, where we stand at the edge of light and realize that the beginning, whatever its ultimate scale, was larger than we once believed, and that we are not lost in it. We are part of it. And in the end, after the telescopes, after the equations, after the speculation about neighbouring bubbles and inflationary landscapes, what remains is something almost unbearably simple. Light travelled. For more than 13 billion years, photons crossed expanding space without knowing whether anything would ever receive them. They passed forming galaxies. They passed exploding stars. They passed entire civilizations rising and falling on distant worlds we will never see. And then, on a small blue planet orbiting an ordinary star, they were caught, measured, interpreted, turned into a question. That is the full arc. Not just galaxies forming too early. Not just inflation refusing to stay contained. Not just the possibility of other universes budding in an endless cosmic foam. But light completing its journey inside awareness. The galaxies JWST spotted may be entirely explainable within our universe's own ferocious youth. Or they may carry the faint imprint of a boundary interaction older than atoms themselves. Scientists are still uncovering which. Data will sharpen. Models will adapt. The tension will either dissolve into revised astrophysics or crystallize into something deeper. But the scale of the moment does not depend on the outcome, because we have already crossed a threshold in human thought. We are no longer asking how many stars exist. We are asking whether reality itself has multiplicity. We are no longer confined to mapping galaxies. We are testing the birth conditions of space-time. And that shift, from mapping objects to interrogating origin, is enormous. Now slow it down completely. Imagine the earliest fraction of a second. A quantum field driving exponential expansion. Tiny fluctuations stretched across incomprehensible scales. Space inflating faster than light could traverse it. In one region, inflation ends. Energy converts to particles. A hot Big Bang begins. That region becomes our universe. Perhaps elsewhere, inflation continues. Perhaps other regions cool into their own Big Bangs. Perhaps not. But here, in this one, structure forms with astonishing speed. Stars ignite within a few 100 million years. Galaxies assemble with surprising maturity. Black holes grow rapidly. Chemical complexity emerges. And billions of years later, matter arranges itself into minds. Minds that can reverse engineer that first fraction of a second. Minds that can ask whether their beginning was singular. That is not a trivial arc. That is cosmic recursion. The universe examining the conditions of its own birth. If there are other universes, they may never know about us. They may expand silently, structureless or unaware. If there is only one universe, then this entire drama, the expansion, the acceleration, the galaxies, the life, the questioning, belongs uniquely to this single unfolding space-time. Either possibility is immense. Either possibility leaves us small in size. But neither leaves us insignificant, because significance does not come from centrality. It comes from participation. And we are participating. We are part of the early universe's long echo. The galaxies JWST sees are not distant strangers. They are ancestors. They are chapters near the beginning of a story that now includes us. Whether they formed under slightly altered initial conditions influenced by neighbouring inflationary domains, or under the unassisted ferocity of our own universe's physics, they helped create the conditions for this moment. This moment where the boundary of the observable feels close enough to touch, where the multiverse is not fantasy, but a mathematical possibility constrained by observation, where the dawn of time is no longer unreachable myth, but measurable epoch. Stand here, on this planet, under this sky, inside this expanding space-time, and feel the scale without being erased by it. The observable universe spans tens of billions of light years. It contains trillions of galaxies. It may be one bubble among countless others, and yet, inside this narrow slice of space-time, matter has become aware of its origin. The early cosmos surged. It built fast. It built large. It left clues in light. And that light has arrived. Whether the final verdict confirms a singular universe or reveals we are one region in a vast multiversal landscape, the emotional resolution is the same. The beginning was not small. The story was not simple. And this small world is not outside that story. It is the place where the story is being understood. Small. Included. Finite in sight, but infinite in possibility. At the horizon of light. Listening to the first galaxies, and discovering that whatever lies beyond, our universe was already extraordinary enough to create the question.